Hi, this is Sarah Razanfer. In this video, I'm going to talk about question number 2 of homework 6 of probability in a stochastic processes course. Let's go to question number 2 and see what is the question. So we have a density, joint density function of x and y, and at first we should find b so that this is a valid joint PDF. To solve this, we should, as always, take the integral with respect to x and y, and this integral should be equal to 1. But at first, I want to do some reparameterization so that I can use r cos theta instead of x, and r sinus theta, r sin theta for y. Uh, okay, after doing the reparameterization, I should use r d theta dr instead of dx times dy, and also the ranges will change. So the theta will be between 0 to 2 pi, and r is between 0 and 1. So, okay, after doing the parameterization and calculating the integral for theta and r, we're going to get to pi times b. Pi times b is equal to 1, so b is equal to 1 divided by pi. Okay, let's go to the second part, b. Find e of x given a specific y, e of x given distribution y, e of y given specific x, e of y given x as distribution, and e of xy. So let's go through the answer. We should calculate all of these. So for e of x, we need to calculate the integral of x, f of times probability density function of x. To calculate the probability density function, we should calculate the integral of f xy with respect to y. So we will get to this, which is f of x, and then times x, and then we should calculate the integral with respect to x, and after that we will get to 0. So the expected value for x is 0, and as you can see uh, in the figure of this distribution, that's really it was somehow expected that we will get to 0. Okay, now let's go to the expected value of x given y. So at first we should calculate the probability density function of x given y, and this is, and from the base theorem we know that it is equal to the probability density function of x and y and divided by probability density function of y. So we have the joint density function, and we have the marginalized density function of y from the previous part, so we will get to this. Now, because we have the probability density function of x given y, we can calculate this integral. So the integral of x times f of x given y, so after doing some calculations, we will get to 0. And again, if we go to this diagram, we see that if x is specific, like the line that we have here, then the expected value is again 0, because these two parts are symmetric, so the expected value is going to be 0. Now let's go to the expected value of x given y as these two are two distribution, we know that the expected value of x given y is a function of y. So if we go through the diagram, we see that if for each value of y, which are the green lines, the expected value of x is 0. So we can say that the expected value of x given y is 0, is a constant value and a 0. And this applies for the expected value of y given x, which is equal to 0. And again, for the expected value of y, we should take the integral of y with the marginalized density function of y. And after doing the calculations, again, we get to 0. And for expected value of y given a specific x, we have this formula, which is the integral of y times f of y given x. And again, after calculating the integral, we're going to get to 0. And for the expected value of x times y, we have the formula times y. We have the formula of the we have this formula that we shall calculate the integral of x times y times the joint probability density function. The joint probability density function doesn't have x or y, so it is out of the integral. And then we should calculate this integral for y and then x. And because y is odd, this is 0, so the complete integral is 0. And for part C, we are asked that whether x and y are correlated or uncorrelated, because the expected value of xy is equal to the expected value of x times expected value of y. So x and y are uncorrelated. Okay, that was my answer to question number 2. Thanks for listening.